Although it is not mentioned by the question the range of values for n, but since we know r starts from 1 and ends at n, so the smallest possible n can go is actually 1, which means that for my mathematical induction here, this equation is going to follow an n that is going to be all positive integers. And to start off my mathematical induction process, I'm going to go for the smallest possible n, which is 1, and to prove that it is going to be true. So if I were to look at P1, the left hand side of P1 is summation from r is equal to 1 to 1 of r plus 2, and this is 1, 1 plus 2, this is 3. And on the right hand side, if I were to let n be equal to 1, so this is 1 over 6, 1, 1 plus 1, which is 2, 2 plus 7, which is 9, so I have 18 divided by 6, this is also 3, which is the same as the left hand side. What we can conclude here is that P1 is true. And since P1 is true, let's make an assumption about Pk. We are going to assume that Pk is also true. For some values of k, that is also going to be positive integers, which means that I'm assuming that the summation from r is equal to 1 to k of r plus 2 is going to be 1 over 6k, k plus 1 and 2k plus 7. And let's write down our aim for the next few processes that we're going to embark on, because what we are trying to prove is that the pk plus 1 expression can also be true. So if we were to prove that pk plus 1 is true, that means we are trying to prove that the summation from r is equal to 1 to k plus 1 of r plus 2 can also be this, where n is replaced by k plus 1. So it can be 1 over 6, replacing n by k plus 1, replacing this n by k plus 1, and then 2 times of replacing n by k plus 1 plus 7, which means that our aim is actually to prove that this is going to be equal to 1 over 6 of k plus 1, k plus 2, and this is 2k plus 9. So if we can achieve this, then our process of mathematical induction is completed. But the thing is, how are we going to achieve this? Are we going to prove that this is equal to this? Nope, not directly from here to here, but how can I prove that this is equal to this through the use of the truth of pk that we have already assumed. So to do that, I'm going to look at the left hand side of my pk plus 1. Left hand side is going to be starting from 1 and ending at k plus 1 of r plus 2. And I'm going to break this up into 2 parts. Rather than from 1 to k plus 1, I'm going to go from 1 to k. That means summing from r is equal to 1 to k of r plus 2. That means I'm going to be left with just one more term, which is the very last term of this summation. And the last term is when r is equal to k plus 1. So here is k plus 1 and k plus 1 plus 2. And what is this? This is what we have already assumed true. So this is 1 over 6k, k plus 1, 2k plus 7, plus what we have here is k plus 1 and k plus 3. Let's take a look at what we need to prove, what we need to show this expression to be. It's got to be equal to this. And here there's a 1 over 6 and k plus 1. So what I'm going to do next is I'm going to factorize out 1 over 6 k plus 1 and 1 over 6 k plus 1 from here. So if I were to factorize out 1 over 6 k plus 1, this I'm going to be left with a k and a 2k plus 7. And here, because I factorize out 1 over 6k plus 1, I am going to have a 6 of k plus 3 here. This is equal to 1 over 6 of k plus 1. And if I were to expand this, this is going to be equal to 2k squared plus 13k plus 18. And this is 1 over 6 of k plus 1, and if I were to factorize this, factorizing this, it will get me k plus 2 of 2k plus 9, which is exactly the same as this. That is why we can say that pk plus 1 is true if pk is true. Because what we are trying to do here is to establish this relationship. I'm not trying to prove that this can be equal to this directly, but I'm trying to prove that this can be equal to this by making use of the truth of the pk's assumption. That is why as long as pk is true, it is going to cause pk plus 1 to be true, and that is the essence of mathematical induction. Which means that since P1 is true, according to this relationship that we have formed, that means P2 is going to be true. And if P2 is true, that means P3 is going to be true, and so on. Okay, that is why with this process that we have done so far, we can conclude that the entire Pn is true through the process of mathematical induction. So, I'm going to conclude by writing the fact that P1, we have already proven that it is true. So since P1 is true, then by this process that we have done, which is the mathematical induction process, I can conclude that the entire series of Pn is true for n to be all positive integers.